We are continuing along with the wave stuff. And actually, we got 3 classes next week because I wanted to meet on Monday, Wednesday, and Thursday for that makeup Monday class. It's on Thursday at 11 a.m. here. So that's a bit weird. But this is sort of a little animated GIF of waves on a field of wheat, and sort of emphasizing that when a disturbance travels along, a wave that y versus x and t, it's not that there's stuff moving in the direction of the wave speed. It's obviously the grass is rooted into the ground, and yet you can sometimes see these waves moving along with the wind. Course evaluations are plugging along. I really appreciate anything you've got to say on there. And I have noticed, by the way, to the video people that you have a little bit less representation than in person. So maybe I definitely care what you think and how this course has been going for the online component. So these are some of the birthdays: Anna, Lehman, and Natalie, and Chris, and Zena. So happy birthday, everybody. Are you one of them? No? Okay. Well, happy birthday. I want to do an example of maybe using transverse waves. Transverse waves on a rope that's stretched to some tension F have a speed of the square root of F over mu, and mu here is called the linear density. It is the mass of the string divided by its length, so it has units of kilograms per meter. I always feel a little surprised. Should we check the units here? Like, it looks ridiculous, right? Let's do a units check. How could it possibly be right? Well, it's newtons per kilograms per meter. A newton, remember F equals ma, means a newton is equal to a kilogram times a meter per second squared. So this is equal to kilograms meters per second squared divided by kilograms divided by meters. So I think what happens is that the kilograms cancel each other, and then the dividing by m comes up to the top, so it's m squared per second squared. And then you take the square root of that, and you get meters per second. So it actually does work. Meters per second. So units, I'll just put a green check mark. Check. Good. Okay. Let's try it. So an 80 kilogram climber hangs from a rope 20 meters below a rocky overhang. The rope has a linear density of 37 grams per meter, which is not an SI unit. So mu is equal to 37 times 10 to the minus 3 kilograms per meter. Don't forget that. Approximately how long would it take a transverse pulse to travel the length of the rope from the climber to the overhang? So I don't know how to draw this, but maybe there's an overhang and then a rope that's going down some 20 meters, and there's a person hanging from it, a climber somehow. I'm not drawing a very good drawing there, but you got it. So this is the 20 meters from here to here. The mass of the person is 80 kilograms. Mu we've got. And I think what's going to happen is there's going to be sort of a pulse that's going to travel up. So maybe he wants to send like Morse code signals to whoever is holding him from above. You hit the rope and a wave will travel up. And the speed of the wave will be determined by the tension in the rope and the mass density of the rope. So V is equal to square root of F over mu, where F is the tension in the rope. I didn't want to use T for tension in this chapter just because we're already using it for the period of waves. So let's do a force diagram of the climber. There's F pulling up and mg pulling down. So if you do sum of all the forces in the y direction is 0 because it's in equilibrium. Once again, plus y is up. You get F minus mg equals 0. So the F equals mg. And then you can just find the V, F over mu. Don't forget to convert everything to SI units. That's sort of important. Assume, also say constant wave speed. So the zero acceleration of the wave. So V is equal to D divided by time. We're trying to find the time, right? So T is equal to D divided by V, which is going to be D times the square root of mu over force or something. So that's actually going to be, since we know the force, mu divided by mg, square root. So T is equal to 20 meters times the square root of 37 times 10 to the minus 3 divided by 80 times 9.8. And I got 0.14, and that should be seconds. Now, what's weird about this, I don't know if you guys have noticed this, we used the mass of the rope, but we also neglected the mass of the rope. We used the mass of the rope to calculate the wave speed, but then when I was considering the force diagram of the climber, well, actually, I think it's okay to neglect the mass of the rope when you're just talking about the climber, because there is an upward tension force, but that's only going to be the tension force at the very bottom of the rope. If you think about the tension at the top of the rope, it's not only suspending the climber, it's also suspending all of the rope, I suppose. So we neglected the mass of rope when calculating tension, which is okay at the bottom, but it's not okay at the top. So that's okay for the bottom of the rope. At the top of the rope, we should add the mass of the rope. I'm kind of wondering, and then it's going to accelerate, I guess, as it goes up, as the pulse goes up. If the tension increases as on the way up, the speed should go on the way up. But I'm just wondering how bad we made a mistake there. We should add the mass of the rope, I guess. So mass of the rope, we can calculate that because we've got 20 meters times 37 times 10 to the minus 3 kilograms per meter. It's equal to 0.7 kilograms, which is not so much. It's much, much less than 80 kilograms. So it's like 80 kilograms is what's being suspended at the bottom of the rope. 80.7 kilograms is what's being suspended at the top of the rope. So maybe there's like a 1% error or something like that in neglecting rope mass. I don't know why I can't write on the bottom of the screen. Sometimes I just like to, when I make an assumption that's bad like that, I like to try to calculate how badly I've done. Like last time when I did the small angle approximation, I assumed that sine theta equals theta. Well, it doesn't quite, but you can kind of subtract and see how bad your error will affect things. Want to do a top hat? This is also on this equation. For a wave pulse on a string to travel twice as fast, if you wanted to make it twice as fast, how would you increase the tension? Think, pair, share. I'll give you a minute to think about that. Discuss. All right. Going once, going twice. People are saying it's increased by a factor of 4. So that's right. That takes into account that square root. If you look at the equation, you have V is equal to the square root of the tension. And so if F goes up by a factor of 4, and then V will go up by a factor of root 4. Okay. So when we send a wave out into the world, we can make it any shape we want depending on how we oscillate that one end, whatever the source is doing. But the one shape that this chapter is totally obsessed about is the sine curve, which looks kind of like this, is a little animation. But basically, over on the left side here, you have simple harmonic motion. That's the choice that you've made to send a wave. You could have sent a triangle pulse or a square pulse, or you could have done an up triangle and a down triangle, but instead you decided to send this sine wave by moving the left end in simple harmonic motion. And so what's interesting is that whatever shape you make, that's what goes out into the world, and that shape remains the same. And if you look at individual particles, on a transverse wave, they just move up and down as this pattern that you've sent is moving past. Well, if you've got a sinusoidal wave, it has a wavelength, which is the distance that the wave repeats over space. You've got the period, which is the time it takes the wave to repeat over time. And frequency is 1 over the period. And the amplitude is the maximum distance, the displacement, I guess, from the equilibrium. So those are the numbers that are important there. Great. And then all these things are related by the wave speed. The wave speed is the rate at which the wave pattern propagates, and it's related to the wavelength and the period, but it's determined by the properties of the medium. So usually what happens is that if you change lambda, it forces a change in the period. Or if you change the period, it forces a change in lambda, because V is fixed by whatever the medium is that you're traveling through. So let me see if I can ask you a couple of questions here. This graph on the right is just kind of showing what happens to a sinusoidal wave as it goes through one period. Well, it goes up and down at the left end, and these crests, I guess, sort of travel along like that from left to right. A traveling wave moves along with a certain speed, wavelength, and period. It was created by an object which is oscillating with simple harmonic motion, like this one is. If the period of the oscillator creating the wave decreases, what should happen to the speed of the wave? A, speed should increase, B, speed should decrease, or C, the speed should remain the same. Just think about that. Check your neighbor. Remember, I think that if the period decreases, that means it's a higher frequency oscillation. So frequency is 1 over the period. Make sure your neighbor agrees with you. Okay. Survey says Okay, so split. Either the speed should increase or the speed should remain the same. I don't know if I can do this one again. I don't know if I can. Well, I guess we can't. But what I think is I got the speed should remain. So it's a little tricky, right? So definitely V is lambda over T. And so you'd think that if you decrease the period that the speed should increase. But if you think about it, that assumes that the wavelength is fixed. Whereas you have this other equation that V is equal to the square root of the tension divided by the mass density of the string. That is actually what's fixed. So V is fixed, and if you change the period, you change the wavelength. So I don't know if you can kind of see it with this rubber hose a bit, but if I do a long period, I'll have a big, long wave that'll go off at some speed. If I have a short period, I'll have tiny little waves that'll go off at the same speed. Okay, so depending on how I shake it, I could shake it, long period or short period. It's a little complicated because we got all these reflections. I'm going to talk about reflections in a minute, but that was a tricky one. So both these equations are true, but the idea here is that this is fixed by the properties of the medium. Not the properties of the wave. So if T goes down, then what happens is the wavelength goes down. Okay? And that's how that first equation still remains true. Okay. Good. Let's do another one. This one's a little, maybe what you're sort of thinking. Traveling wave moves along with a certain speed. Wavelength. The period is created by an object which is oscillating with simple harmonic motion. If the period of the oscillator creating the wave decreases, what should happen to the wavelength of the wave? Okay. Let's see what people are saying. Let's see if this one went better. Yeah, you got it. We kind of went over that. But yeah, basic idea. It is that, again, V is equal to lambda over the period. So lambda is equal to V times the period. So, and again, the moral of the story is that the speed of the wave in a medium depends on the properties of a medium, not the properties of the wave, I guess. So there's a pretty good animation that goes through a lot of this stuff on the web. It's called PHET. These are some interactive simulations that were produced by University of Colorado Boulder. But I'd like you to go and give it a try because on Monday morning there's a pre-class quiz, and one of the questions in the pre-class quiz is to answer question 7 from this little pre-class homework. That's all it is. There's no other, it's not submitted in any other way than just the pre-class quiz. But I think it's good to give it a try. You're actually going to end up making sort of standing waves. But the basic idea here is we're getting into wave reflection. So with a single pulse, if you send it towards a boundary like the one we have here with the rubber hose where it's tied onto the end, then when the incident wave pulse hits the end, it kind of bounces off the end. What the end does is it fixes the momentum, and so it produces, if the string is trying to pull the end of it up, then there's a force from the post at the end, I guess where the knot is, pulling it down. And that force causes it to overshoot at the end, and you get a negative pulse that reflects back. And you can clearly see that whenever, you've probably noticed it as I'm doing this, because that's exactly what we've set up here. If I send a positive pulse from left to right, and so video guys, you might need to turn off my PowerPoint and then center me so you get the whole, if we can do this. So did you see the pulse that came back was inverted? And then when it hits my hand, it inverts again. Every time it hits a fixed end, the pulse flips its shape. But, so that's a fixed end. If you, there's another way of, so with a single pulse like this, you can see the reflection. And for a sinusoidal wave, the waves begin to overlap. And so actually we should try that. What if you send a sine wave by oscillating this with simple harmonic motion? Well then, it doesn't do, I don't know. It's not as all what I expected would happen. It's just going up and down. So, and you can, anyway. There's probably multiple reflections that are happening. You got to try this out when you actually do the simulator. But if I increase the frequency, I can get more of these. I don't know if you've ever done like skipping rope or something like that. You can do it with circles too. Anyway, so something weird definitely happens. We're going to talk, that's called a standing wave, and we'll talk about standing waves when we come to next class. Next week. All right. I was going to say, you can hold the tension in the rope in two ways. One is you could tie the rope like a string, so it's sitting there. The other one is that you could have a frictionless pull and a little ring, so it can slide up and down. Then what happens is that there is no vertical force on the rope from the end, so its inertia just carries it up, actually past its normal amplitude. It's twice the amplitude of the pulse. The ring shoots up because there's no tension on the other side, pulling it back down. And what that does when it comes back down is it creates a positive pulse that gets reflected. So that's called a wave reflection from a soft boundary. And you can also have two different thicknesses of rope that are tied together, so the tension is the same on both sides, but what changes is the wave speed, and this acts like a boundary. Every time there's a change in a medium from one region to another, and there's a boundary, and a wave comes along, that generates a reflection and a transmission. So whatever wave energy comes along in that original pulse, it's split at the boundary. Some of it goes into the second medium, and some of it gets reflected back to the previous medium. You can kind of see this with glass, right? If you have light shining on glass, I guess a lot of it goes through, because glass has a different speed of light than the air, but some of it gets reflected. You can always see a little reflection coming off of it. It's the same sort of thing. You're changing the speed, so there's a transmitted wave and there's a reflected wave. But if the second medium is thicker and it poses more inertial resistance to the up and down motion, you end up with an inverted pulse, kind of bounces off again. The reflected pulse is inverted. And if you do the opposite and you have a medium that's thinner, then it's got less inertia, it overshoots, and it produces a positive reflection like that. See, the one on the left is now positive as opposed to negative. And that sort of came up on this morning's pre-class quiz. A wave pulse traveling to the right along a thin cord reaches a discontinuity where the rope becomes thicker. The reflected pulse is then inverted. And the transmitted pulse is always going to be the same, I guess, sign as the original pulse. Okay. You guys doing okay out there? All right, so we're getting into sound, and this textbook kind of tries to put all the sound stuff into one section, but to me, sound sort of has two really interesting properties. It has loudness and frequency. And so today we're going to talk about the loudness of sound, and then on Monday we'll talk more about the frequency. Sort of the way I'd like to do it. Not quite the way the book does it. But if you have a speaker's power is measured in watts, and it's putting some energy. A watt, remember, is a joule per second, so it's putting some amount of energy per second out into the sound, into the air. Wave fronts are spheres, I guess, or I guess maybe hemispheres in this case, if it's going off in one direction, if it's up against a wall. And if you have a hemisphere, its area is measured in meters squared. So we have a new quantity called intensity, which is power per area. And the units here are going to be watts per meter squared. And the way it looks, intensity of a wave is the average power it carries per unit area. If the wave spreads out uniformly in all directions and no energy is absorbed, then the intensity at some distance r from the source decreases as 1 over r squared. Inversely proportional. So the way it looks is, if it's a whole sphere there, then its intensity is equal to the power divided by 4 pi r squared, because 4 pi r squared is the surface area of a sphere. And so if you're listening to some source at a distance r, then, and it's putting out some power, that power will be spread out, if it went in all directions, over a sphere of radius r that has a area 4 pi r squared, and you'll just hear a little bit of it. Like, does that sort of make sense? Here's my ear, which has a certain collection area, I guess. Maybe I don't know what part of my ear is really important here, but point is that it's got some area. Maybe my eardrum has a certain area which will catch a certain amount of power. So if I stand farther away from the same source and that power is spread over a bigger area, I'm going to catch less of it with my ear. And that's why farther things are quieter. It's not because the energy went away, it's just because it got more spread out on the way to us. That's where the 1 over r squared thing comes from. We'll do a top hat, but let's look at it another way. Sometimes I go through these things a couple of times, but we can think of, we've been talking about spherical waves. You can also imagine like a plane wave. It doesn't spread, so its intensity remains constant. So if some wave fronts are just these parallel planes going along, then it'll still have some sort of wave intensity, but it'll remain constant with distance. But a spherical wave, if you look at some, I guess, little portions of it, as you get farther away from that source, the area gets bigger and bigger. So if the power is constant, then the intensity decreases with distance. So let's do a little top hat question. I don't know if this sends a little picture to your phone. So this is an imaginary bubble. So what I am asking you to picture in your head is that there's a big room, huge room, and hanging in the center of the room is a speaker, which is got it's 20 watt. It's outputting 20 watts of sound energy, or 20 joules per second of sound energy. And you're standing 9 meters away from it. So if you imagine a big sphere, it's an imaginary sphere, which is centered at the speaker, and the edge of the sphere is at your ear, it'll have a radius of 9 meters and a surface area of, I think I worked it out, it's 4 pi, that's 4 times 3.14 times 9 squared. I think that gets to be 1,000. So the question is, what's the intensity that reaches your ear? So the concept is, you got the intensity is the total power divided by the area that's spread out over. So you take 20 watts and divide it by the surface area of that sphere, and that will be the intensity that's at your ear. So your ear is a detector of intensity. Higher intensity, louder it sounds. So that was good. You guys get me? What am I doing here? So So weird. It's weird. Remember, sound waves are longitudinal mechanical waves that propagate through gases, liquids, and solids. And sound waves in air involve small changes in air pressure that are associated with this back and forth motion. So I don't really see intensity anywhere on this, but I will just say that the intensity is related to the amplitude. So the intensity, which is in watts per meter squared, is related to the amplitude of the wave, which is in pascals, I guess, is the pressure. I'm not going to really say how it's related. It's kind of complicated, but this is the basic idea. Low volume is you've got little changes in the air pressure. High volume is you got bigger changes in the air pressure. So this is a low intensity sound wave. Sound wave. So the number of watts per meter squared is low when it's just a little bit of shaking of pressure. But when you take that same wave and just increase the pressure variations, now you're carrying more energy per meter squared, high intensity. It is not at all obvious how you switched from one to the other, but that's the basic idea. Okay, and so now there's this whole thing about intensity level. So let's go over that. Intensity versus intensity level. I really feel like we should have come up with maybe a different name, but these are completely different, but they're describing same sort of thing. The decibel, abbreviated dB, is the unit used to measure the intensity level of sound. The decibel scale is based on, I don't know what it's based on exactly, but it's something to do with the fact that the human ear is sensitive to a large range of intensities. So if you think of the quietest sound you can hear versus the loudest sound you can tolerate without getting ear damage, there's a factor of about 10 to the power 12, so about 1 trillion in intensity. It goes from 10 to the minus 12 watts per meter squared up to about 1 watt per meter squared at like a rock concert or something like that. So that's a big difference. So we've introduced this thing beta, which is 10 times the base 10 logarithm of intensity divided by I0, where I0 is this reference intensity of it's called the threshold of hearing, 10 to the minus 12 watts per meter squared. So basically, I don't know if you know, log of 1 is 0, so 0 in decibels would be when I equals I0. So you got 10 to the minus 12 watts per meter squared. Logarithm of I0 over I0 is log of 1, which is 0. That's 0 decibels, so it's the quietest thing. Then if you increase the intensity by a factor of 10, you get the logarithm of 10, which is 1. And you multiply by 10, you get 10 decibels, that's 10 times more powerful. But if then you'd think it would go to 100, it doesn't. It goes to 20 when you increase by another factor of 10, because the logarithm of 100 is 2 times 10 is 20, etc. 1,000 would be 30 decibels. And you can also invert this. I don't know if you guys know, if somebody gives you the intensity level beta, intensity, and they want you to compute the intensity I, you can divide both sides by 10, and then use the fact that definition of logarithm base 10 is that 10 to the log x equals x. So you can take logarithm of both sides, 10 to the power of both sides, and you get 10 to the power of beta over 10 equals 10 to the power of log thingy, and then which is just I over I0. So then you solve it out for I. I is equal to I0 times 10 to the beta over 10. So I would actually put both of these on your aid sheet. These are two useful equations, depending on which you're given, right? And it should be able to hopefully press the log button on your calculator. So a student this morning asked, why do we need to calculate the intensity level? Why is it necessary? And that is a really good question. I don't think it really is necessary. So, and the way I put it is that if the world was populated entirely by physicists, then this particular Toronto bylaw would read, motorcycle noise cannot exceed the approved standard of 1.6 times 10 to the minus 3 watts per meter squared from the exhaust while the motorcycle. So that's not what the bylaw reads. It reads just 92 decibels. And so I think sound engineers long ago just got tired of doing the 10 to the minus 12 watts per meter squared. And so they came up with this scale to shorten it, I guess, a bit. But anyway, for that reason is why I'm studying decibels. It is kind of important if you're going to deal with other humans who are not in the physics department. But I don't know, it's really all that matters is the intensity, right? And so the intensity level is just a system that we've developed to kind of tell people what the intensity is. There's the table from your book, and what's interesting here, what you note here is that for every multiplicative factor of times 10 in the intensity, which is the real thing, the watts per meter squared, you end up with a plus 10 in the decibel scale. That's how a logarithm works. But I guess you can sort of see the intensity level in decibels is a little more convenient to deal with, since we're dealing with these things, normal breathing, quiet office, Niagara Falls, jet engine. You can put a decibel level in all this, and it's just a bit more convenient than writing all the 10 to the minus stuff. It's a great question. Let's look at this morning's pre-class quiz. The intensity of sounds in a quiet classroom is 10 to the minus 7 watts per meter squared. The intensity of sounds in busy traffic is 10 to the minus 5. By how many times is the intensity of traffic, intensity, traffic, divided by I, classroom? So I'd say it's going to be 10 to the minus 7 divided by 10, traffic corrects, 10 to the minus 5. All right. So it is important that you guys know how to use your calculator when you do this sort of stuff. I press escape and pull up my calculator. On my calculator that's up here, I would type, so 10 to the minus 5, I would type 1 exp 5 negative. That means 1 times 10 to the power minus 5, right? That's what the little e means on my calculator. And then I press divided by 1 exp 7 negative. I got 100. You might know that, but just want to make sure everyone's using their calculator all right. Whoop, 100. So that's where that comes from. Okay, next question was, intensity level of sounds in a quiet classroom is 50, whereas traffic is 70. By how many times is the intensity? So that's another thing, is that, so 70 minus 50 is 20, which is equal to 10 plus 10. This is 2 additive steps in decibels. And what this corresponds to is 2 multiplicative factors of times 10 in intensity. You could just do the logarithms, I guess, but that's the way that's why it's 100. Okay. Got a little bit of time for another one. See if you guys can do these two. One singer produces an intensity of 10 to the minus 4 watts per meter squared when she sings at a distance of 3 meters from a listener. So it's important to include the distance, right? Because farther away will be less intensity. If you get 10 singers together who sing at the same volume at the same distance, what would be the intensity? So idea being that every singer produces a certain amount of power, and I think they'll all kind of add up. If there's 10 of them, it'd be 10 times as many watts, right? I think it is 10 to the minus 3. So the way I did it, and I guess I'll bring up my calculator again, is that I1 is whatever it is. Well, it's 10 to the minus 4. So that's 1 times 10 to the minus 4. So if I bring up my calculator again, I'm going to go clear 10 x 1 EE, sometimes it says, and then 4, and then negative sign equals, it's 0.001. So that is equal to 10 to the minus 1, 2, 3, and minus 3. Okay. Good, so it's A. Next question is one singer produces an intensity level of 80 decibels. So if you get 10 singers, what's the intensity level? There's a lot of different ways of doing this, but my idea here is just that since the intensity has increased by a factor of times 10, because there's 10 times as much power, so 10 singers. Like the real thing is the intensity, right? 10 singers means 10 times the power. And if they're at the same distance, and so 10 times, I'm not sure how 10 people can stand at the same distance, but maybe it's possible. So 10 times the intensity. We're all in a tight little area somehow. So what that means is you have a plus 10 in decibels. So the new beta of 10 will be beta of 1 plus 10. So it's 80 plus 10 is 90 decibels. That's one way of doing it. So that's all I got. I hope you guys have a great weekend. Please try the do-it-yourself demonstration on the link there to the simulation. It's kind of fun. You'll hopefully create your own standing waves by the end of it and come up with a good frequency for question 7. And that'll be in your pre-class quiz on Monday morning, and I'll see you back here. Have a good one.